Penrose and the eternal cosmos. What if the universe never truly dies, but instead begins again? What if time itself is recycled? Every Big Bang just a new movement in an endless cosmic rhythm. Welcome to Sleep Entangled, where science and reflection meet in quiet wonder. If you enjoy exploring the deep questions of physics and consciousness, subscribe and join us on this journey through the strange continuity of existence. Tonight, we'll explore one of the most intriguing cosmological ideas of our time, Sir Roger Penrose's theory of conformal cyclic cosmology, a model suggesting that our universe is just one of many aeons, each rising from the ashes of the last. We'll trace its logic, evidence, and implications, and what it could mean for the future of everything, the end that isn't the end. In most cosmological models, the universe began with the Big Bang and will eventually end in one of three ways: a slow heat death, a violent crunch, or an eternal expansion into cold darkness. Penrose looked at these scenarios and asked a simple but unsettling question: why must time stop there? As the universe expands, matter thins, energy disperses, and all motion slows. Stars die, black holes evaporate, and even atoms decay. At first glance, this sounds like an ending, a universe stretched so thin that nothing meaningful remains. But Penrose saw something different. He imagined that in this far future, when the universe becomes uniform and empty, the concepts of distance and scale lose meaning. Without matter to define them, there is no longer a sense of big or small, only geometry, pure, scale-free geometry. And when scale no longer matters, something remarkable happens. The infinite future of one universe can mathematically resemble the beginning of another. Conformal Cyclic Cosmology, a universe in echoes. Penrose called this idea Conformal Cyclic Cosmology, or CCC. In this model, the universe evolves through a sequence of aeons. Each aeon begins with a Big Bang and ends in a vast, empty expansion. But that end becomes the Big Bang of the next aeon. Imagine an infinite chain of universes, each connected not by destruction, but by transformation. The geometry of space-time, stretched beyond measure, folds seamlessly into a new beginning. It's not reincarnation. It's more like the universe breathing, expansion, silence, renewal. Penrose was drawn to this model partly because of a deeper conviction that physics must ultimately be geometric. He has spent his life searching for patterns that link space, time, and consciousness through geometry, not randomness. CCC, to him, was an elegant continuation of that vision, the simplicity beneath the complexity. The idea sounds radical, but Penrose's logic is simple. At the end of the universe, everything with mass disappears. Black holes evaporate through Hawking radiation, leaving only photons, particles of light that have no mass. Without mass, there's no concept of time or size in the usual sense. Whether something is a meter wide or a million light years wide becomes irrelevant. The universe becomes scale invariant. At that point, Penrose argues, it's mathematically possible to squash infinite time into a new beginning. The transition doesn't involve a singular explosion, but a kind of smooth morphing, the infinite future of one cosmos becoming the Big Bang of the next. A radical idea meets resistance. Where we? When Penrose first introduced CCC, many cosmologists were skeptical. The Big Bang, after all, is one of the best tested theories in science. Observations of the cosmic microwave background, galactic motion, and the abundance of light elements all fit beautifully into a standard cosmological picture. But Penrose wasn't trying to replace the Big Bang. He was extending it. He suggested that the bang we see might not be the first or the last, but one in an infinite series. This, of course, raised questions. If universes keep emerging, Could any trace of the previous one remain? Could we, in principle, detect fingerprints of an earlier cosmos? That challenge, finding physical evidence for an idea so grand, would become central to Penrose's later work. Looking for ghosts in the sky. Penrose proposed that if one universe gives birth to the next, subtle imprints could survive in the cosmic microwave background, the faint radiation left over from the Big Bang. He predicted circular patterns, concentric rings, where energy from supermassive black holes in a previous aeon might have leaked through the boundary into ours. In theory, these Hawking points would appear as slightly warmer regions in the CMB, surrounded by faint halos. In 2010, Penrose and physicist Vahe Ghourzadyan claimed to have found such circles in satellite data from WMAP and Planck. They described regions where temperature variance was lower than expected, possible evidence of events older than our universe. The reaction was immediate. Some researchers found the analysis intriguing. Others argued that the patterns were statistical noise. Subsequent studies offered mixed results. Some found weak support, others none at all. Even today, the debate continues. Are these rings proof of a universe before ours, or just random ripples in cosmic background radiation? Penrose himself remains cautious, but optimistic. It's not conclusive, he says, but it's a hint, and hints matter. A universe without a beginning. One of the most striking consequences of CCC is its treatment of time. In most cosmological models, time begins with the Big Bang. Before it, the word before has no meaning. But in 330, there is no ultimate beginning, only transitions. Each aeon inherits the geometry of the last, and so time, in a sense, never starts. It just changes form. This challenges not only physics, but philosophy. If there was no first moment, what does creation mean? What does it mean to speak of origins when everything is cyclic? Penrose's answer is pragmatic. He doesn't frame CCC in spiritual or metaphysical terms. For him, it's simply a logical consequence of how geometry behaves when scale vanishes. It's less about mystical rebirth and more about mathematical continuity. Still, the implications are enormous. If time is cyclical, then everything, galaxies, stars, perhaps even the seeds of life, may emerge again and again in endless variation. Entropy and the arrow of time. To understand CCC, we need to touch on entropy, the measure of disorder. In thermodynamics, entropy always increases. It's why ice melts, why coffee cools, why stars burn out. It gives time its direction, forward. But the early universe, right after the Big Bang, had remarkably low entropy, almost perfect order. How did such a highly ordered state arise? This question has puzzled physicists for decades. Penrose believes CCC offers an elegant answer. If each aeon ends in a state of complete uniformity, zero gravitational structure, zero entropy, then the next aeon begins naturally in a low entropy condition. The arrow of time resets itself at every cycle. In other words, the mystery of the universe's low entropy beginning might simply reflect the death of the previous universe. Philosophy meets physics. Penrose has always been an outlier in science. A mathematician who sees beauty in geometry. A physicist who refuses to separate logic from imagination. He's skeptical of theories that multiply dimensions or rely on unobservable entities. His models, no matter how bold, always aim for conceptual clarity. CCC fits that pattern. It doesn't require parallel universes, hidden strings, or multiverse speculation. It simply says, the universe continues, governed by the same equations, through transformations of scale. It's a minimalist infinity, one cosmos, endlessly reborn. Critics point out that CCC remains difficult to test. Supporters counter that so was general relativity, for decades, until technology caught up. As with many of Penrose's ideas, time will tell, literally. From black holes to new beginnings, black holes play a special role in Penrose's thinking. In his earlier work, he showed that singularities, points where space and time collapse, are inevitable in any realistic universe. In 330, black holes are not the end, but the transition. They evaporate slowly through Hawking radiation, releasing their energy into the empty cosmos. That energy becomes the seed of the next Aeon's beginning. It's a poetic symmetry, the death of stars giving rise to the birth of new worlds. But again, Penrose insists it's not poetry, it's geometry. The mathematics of curvature and conformal transformation make the transition possible. And this perspective reframes our own place in time. We are not living in the universe's first act, nor its last. We are a chapter in a much larger book, written in the language of space-time itself. A thought experiment before sleep. Picture a blank canvas stretching infinitely in all directions. Over countless billions of years, color fades, edges blur, and every trace of structure vanishes. Then, imperceptibly, that blankness folds in on itself and becomes a spark of light. That spark grows, expands, cools, and eventually fades again. Each cycle is distinct yet continuous. No God, no beginning, no end, only transformation. It's a humbling vision, but also a comforting one, because in Penrose's universe, nothing is truly lost. Every atom, every photon, every trace of information will someday find a new stage, a new role, a new Aeon. The cosmos may never sleep. Its story continues through ages uncounted, and you, a brief consciousness within it, are part of that endless rhythm. In the next chapter, we'll follow how Penrose connects this eternal geometry to something even more personal, the mystery of the mind itself. Chapter 2. The geometry of consciousness. What if consciousness isn't a byproduct of the brain, but a reflection of the universe's geometry itself? If these calm, deep dives help you think, or fall asleep a little wiser, subscribe and let curiosity guide your rest. A physicist obsessed with form, Roger Penrose has always believed that the universe's deepest truths are geometric. He doesn't just see shapes, he sees relationships, patterns that reveal how reality holds itself together. From his early work on black holes to his ideas about the human mind, Penrose returns again and again to one conviction. Mathematics isn't just a language we invented. It's the structure of reality itself. This conviction drove him to question a simple assumption, that the mind is just a biological computer, running algorithms in neurons like circuits in a chip, the limits of computation. In the late 20th century, artificial intelligence was gaining ground. Many scientists argued that the brain was essentially a computer, just a more complex one. Feed it data, process it through neurons, get output, thoughts, decisions, emotions. But Penrose disagreed. He pointed to the work of mathematician Kurt Gödel, whose incompleteness theorem showed that in any formal system, there will always be truths that can be seen to be true, but cannot be proved within the system itself. That insight bothered him. If mathematics, the purest form of logic, contains truths that no algorithm can reach, then how do humans see those truths? How can a brain, supposedly just a machine, recognize something a computer never could? This, he argued, meant that human understanding involves something beyond computation. Gödel's ghost in the machine. Penrose often gives a simple example. Imagine a mathematical system that can generate proofs mechanically. For every statement, it either finds a proof or declares it unprovable. Gödel showed that within such a system, there will always be a statement that is true, but the system itself cannot prove it. Yet humans can see that it's true. We can step outside the rules of the system and recognize a truth the machine cannot reach. Penrose called this insight a clue. Human consciousness, he argued, must involve non-computable processes, something that transcends algorithmic logic. And whatever that something is, it must have a basis in physics. That idea set him on a collision course with both neuroscience and computer science, the search for a physical foundation. If consciousness isn't computation, what is it? Penrose's answer came from his lifelong study of geometry, particularly the geometry of space-time itself. He proposed that consciousness arises from quantum processes within the brain, specifically within microscopic structures called microtubules inside neurons. These microtubules, he believed, could act as quantum systems, maintaining coherent states that collapse in orchestrated ways, producing what we experience as awareness. This became the foundation of his collaboration with anesthesiologist Stuart Hameroff, leading to the theory known as orchestrated objective reduction, or OR, a topic we'll explore in depth in the next chapter. But before we get there, it's worth understanding why geometry, not computation, is so central to Penrose's thinking. Geometry as the language of reality. For Penrose, geometry is not just the backdrop of physics, it is physics. Space, time, gravity, and quantum behavior all emerge from the way geometry bends and interacts. He once wrote, "To understand the universe, you must understand shape." This conviction led him to develop mathematical tools that visualize complex concepts, like Penrose diagrams, which map the causal structure of space-time, showing how light and matter move near black holes or across cosmic horizons. But he didn't stop at cosmology. He wondered, if geometry governs the universe at every scale, might it also govern the structures within the brain? Could the geometry of microtubules, those lattice-like frameworks inside neurons, be designed by evolution to harness the same physical principles that shape the cosmos, a bridge between scales? Most scientists see the universe and the brain as separate domains. Cosmology studies the vast, neuroscience studies the small. Penrose's view bridges the two. To him, consciousness isn't a local accident. It's part of the same underlying geometry that shapes galaxies and black holes. That may sound abstract, but the principle is simple. The same equations that describe gravitational curvature might, at another scale, describe patterns of thought. This is why Penrose has always resisted reducing the mind to computation. A computer manipulates symbols. It does not know what they mean. Consciousness, however, involves meaning, intention, and understanding, qualities that seem to require a deeper connection between matter and information. Geometry, he believed, could be that connection, the bridge where physics becomes experience. Quantum geometry and objective reduction. Here's where the physics enters. In quantum mechanics, a particle exists in a superposition, a set of possibilities, until it is measured, and the wave function collapses into one outcome. For decades, scientists have debated what causes this collapse. Is it the act of observation, random chance, or something deeper? Penrose proposed that collapse is an objective process, something built into the structure of reality itself. When two states of matter differ too much in their gravitational configuration, when their mass distributions warp space-time in incompatible ways, nature resolves the conflict by collapsing one into the other. This is objective reduction. Now, if such collapses occur in orchestrated patterns, guided by the geometry of microtubules, they might produce consciousness. The idea is bold, but elegant. Awareness as a physical process tied to the curvature of space-time. Why the brain, and why microtubules? At first, Penrose didn't know where in the brain such quantum processes could occur. That's where Hameroff came in. Hameroff pointed out that microtubules have a structure strikingly similar to certain quantum lattices, ordered yet dynamic, capable of oscillations and resonance. Unlike the messy chaos of synaptic firing, microtubules form regular arrays that could, in theory, sustain quantum coherence. If they do, then every neuron isn't just a switch, it's a tiny quantum computer embedded in a biological network. this is where geometry returns once more. The patterns within microtubules, the symmetries of their protein lattices, might allow for stable quantum resonance, like standing waves in an instrument string. The music of these resonances could, Penrose and Hameroff propose, be the music of consciousness itself. Critics and common ground. Critics argue that this is speculation without strong evidence. The brain, they say, is too warm and wet for quantum coherence to survive. And yet, discoveries in quantum biology, such as coherence in photosynthesis and entanglement in bird navigation, have begun to erode that assumption. Even if Penrose's exact mechanism is unproven, the broader idea that life exploits quantum effects is now accepted science. And this lends weight to his belief that consciousness may be another layer of that same evolutionary pattern. Some researchers even suggest that microtubules could be involved in the brain's electrical rhythms, coordinating neural firing across regions, a classical counterpart to the quantum orchestration Penrose envisions. So while his full model remains controversial, its components keep finding new life in research. Mathematics, meaning, and mystery. At the heart of Penrose's vision lies a question that blends mathematics with philosophy. Why does math describe the universe so perfectly? To him, it's because math and reality are not separate. The geometry of the universe is not an abstraction, it is the universe. And when consciousness arises, it's not emerging from chaos, but from that same deep structure. In that sense, your thoughts are not floating illusions. They're events within geometry. The mind, in Penrose's view, is the cosmos thinking through itself. A real-world perspective. In 2020, Penrose won the Nobel Prize in Physics for his work on black holes, recognition of his genius, and his lifelong belief in the power of geometry. Yet when asked about consciousness, he remains modest. "We don't know," he says, "but it must involve new physics." That humility is key. Penrose doesn't claim to have solved the mind-body problem. He simply argues that the current models, purely computational or chemical, are incomplete. To understand the mind, we must include geometry, quantum processes, and gravity itself. This is not mysticism, it's curiosity pushed to its limits. An analogy before rest. Imagine a calm lake at night. On its surface, ripples spread from raindrops. The waves interfere, merge, and fade. Now imagine that the water itself is space-time, and the ripples are moments of awareness, patterns emerging from the lake's geometry. The waves aren't separate from the water. They are the water expressing itself. Consciousness, perhaps, is the same. The universe experiencing its own geometry through the structure of the brain. The shape of your thoughts might not just reflect the brain, but the structure of reality itself. In our next chapter, we'll dive into the heart of Penrose and Hameroff's theory, orchestrated objective reduction, and see how it could connect the physics of space-time with the experience of being. Chapter 3, Orchestrated Objective Reduction, OR. Could consciousness be a physical process, not magic, not mystery, but quantum physics happening inside your brain? We'll break down Penrose and Hameroff's orchestrated objective reduction theory, what it proposes, how it works, what critics say, and why, even after decades, it refuses to fade from scientific discussion. The meeting of minds. The story of OR begins not in a physics lab, but in a hospital operating room. Stuart Hameroff, an anesthesiologist, spent years observing something strange. When patients are put under anesthesia, brain activity doesn't stop. Neurons still fire, electrical rhythms continue, chemistry flows, yet consciousness disappears. The light goes out, and then, when the drug wears off, it comes back on again. Hameroff began to wonder, what exactly are these drugs switching off? If neurons still fire, maybe consciousness isn't just about signals traveling between them. Maybe it's happening somewhere deeper, inside the cell itself. That question caught the attention of Roger Penrose, who was already convinced that human thought involved non-computable physics. Together, they formed one of the most unlikely collaborations in science: a physicist obsessed with geometry and a doctor fascinated by the biology of awareness. Their shared question: could the secret of consciousness lie in quantum mechanics? The framework: objective reduction. To understand OR, we start with Penrose's earlier work on quantum mechanics. In standard quantum theory, particles exist in superpositions, multiple states at once, until they're observed or measured, causing their wave function to collapse into a single reality. But this collapse has always been mysterious. What counts as an observation? Why should consciousness cause it? That question haunted physicists for nearly a century. Penrose offered a new answer. He proposed that wave function collapse doesn't require an observer. Instead, it happens objectively when superposed states differ enough in their gravitational configuration. Two possible realities, each with different mass distributions, create a tension in space-time. When that tension exceeds a threshold, nature itself resolves it by collapsing the wave function, selecting one reality over the other. This is objective reduction, OR. It means quantum collapse is a physical process, built into the universe. Now imagine billions of such collapses happening inside the brain, not randomly, but in harmony. That orchestration, Hameroff suggested, could be consciousness. Microtubules, the quantum stage. Inside, every neuron lies an intricate scaffolding made of protein tubes called microtubules. They form the internal framework of the cell, guiding molecular transport and helping it keep shape. Hameroff noticed something about these structures. They weren't just mechanical supports. Their protein subunits, called tubulins, could exist in two or more conformational states. In other words, they could switch between configurations, like bits in a computer or qubits in a quantum computer. Each tubulin, he suggested, could store and process information, and the entire lattice of microtubules could act as a massive network of quantum computation. This idea was radical. It meant consciousness might not arise from neuron to neuron communication at all, but from quantum processes happening inside neurons, at a level far smaller and faster than traditional neuroscience could measure. In this view, the brain isn't just an electrical organ. It's a biological quantum computer. The orchestrated part. The word orchestrated in OR refers to how these quantum collapses might be coordinated. Hameroff believed that microtubules within neurons could communicate through vibrations, coherent oscillations at specific frequencies, creating resonance across the brain. When these oscillations align, vast numbers of microtubules might undergo objective reduction together, a synchronized collapse that produces a unified moment of conscious experience. This process would repeat many times per second, creating a continuous flow of awareness, like frames in a movie forming a seamless picture. Each collapse, Penrose argued, corresponds to a discrete moment of consciousness. Billions of such moments, orchestrated together, become the inner movie we call the mind, from physics to phenomenology. This is where OR becomes more than a physics model. It becomes a theory of experience. Most physical theories describe matter. OR attempts to describe awareness. It bridges subjective experience with objective process, proposing that every conscious moment is a quantum event, shaped by the geometry of space-time itself. In this view, your awareness is not merely neurons firing, it's the universe resolving uncertainty inside your brain. Every thought, every perception, every decision could be the physical manifestation of a quantum collapse, a moment when space-time chooses a definite state, and you experience it as now. The evidence so far. For decades, OR was dismissed as speculative. Critics pointed out that quantum coherence is fragile, easily destroyed by heat, noise, and biological complexity. The brain, they argued, is far too warm and chaotic to sustain it. But recent research has begun to challenge that assumption. In 2014, physicist Anirban Bandyopadhyay and his team at the National Institute for Materials Science in Japan detected coherent vibrations in microtubules at frequencies in the megahertz to gigahertz range, potentially compatible with quantum processing. Later studies showed that anesthetic gases disrupt these vibrations, echoing Hameroff's early observations in medicine. While not definitive proof, these findings reopen the discussion. The possibility that microtubules could support coherent quantum states under biological conditions no longer seems impossible. In quantum biology, coherence has been observed in systems as diverse as photosynthesis, bird navigation, and enzyme catalysis, all warm and wet environments once thought too noisy for quantum effects. The line between too delicate and just possible keeps moving. The anesthesia connection. Hameroff's background in anesthesia gave the theory a fascinating biological angle. Anesthetic drugs, such as halothane and xenon, can eliminate consciousness without shutting down all brain activity. They don't stop neurons from firing. They interfere with something more fundamental. Hameroff proposed that anesthetics act on the microtubule lattice, binding to tubulin and disrupting its quantum coherence. In effect, they break the orchestration, scattering the rhythm that generates awareness. When the drug wears off, coherence returns, and consciousness boots up again. This mechanism fits both clinical observation and Penrose's physics. The quantum processes that create awareness are reversible, unless permanently damaged. It's a rare case where a quantum hypothesis might explain a medical mystery. Criticism and counterpoints. Of course, the theory has faced resistance from mainstream science. Neuroscientists argue that the brain's known mechanisms, neural networks, feedback loops, neurotransmitters, already explain consciousness without invoking quantum mechanics. Others say the math behind OR is incomplete, or that its timescales don't align with observed brain rhythms. Penrose and Hameroff acknowledge these gaps. They argue that the model is still evolving, and that experimental evidence is catching up. In science, bold ideas often precede the tools needed to test them. Even if the full model proves wrong, its influence is undeniable. It's pushed neuroscientists, physicists, and philosophers to rethink what consciousness might be, not as an emergent illusion, but as a process intertwined with physical law. A broader context. To place OR in perspective, it helps to remember the alternatives. The dominant view, materialist neuroscience, holds that consciousness emerges from computation. Information processing in networks of neurons eventually crosses a threshold of complexity and self-reference, giving rise to awareness. This model works well for simulating intelligence, but it struggles to explain experience. Why should computation feel like anything? Why does information become self-aware? This is known as the hard problem of consciousness, and OR is one of the few theories that attempts to tackle it head-on by linking subjective experience to fundamental physics. If true, it would mean consciousness isn't an accident of evolution. It's a basic feature of the universe, expressed through biology. The cosmic connection. Here, Penrose's cosmology returns. If the same geometry governs both space-time and the brain, then consciousness might be a cosmic phenomenon, localized, yes, but connected to a universal field of quantum processes. In 300, each universe is born from the geometry of the last. In OR, each conscious moment arises from the geometry of space-time. Both theories see continuity where others see separation, between life and matter, between thought and physics, between endings and beginnings. In that sense, your awareness might not just be of the universe. It might be within the universe, a local manifestation of a global principle, a thought experiment. Imagine consciousness as a symphony. In the classical view, neurons are the instruments, and the music is computation. Predictable, mechanical, encoded. In OR, the symphony runs deeper. The instruments themselves are quantum resonators, and the music arises from the collapse of quantum states. Each note is a choice the universe makes, a reduction of possibility into reality. Every thought is a note in that cosmic score. The melody is fleeting, but it's real, played across billions of microtubules, orchestrated by physics itself. The legacy of OR. After more than 3 decades, OR remains controversial, but it refuses to disappear. It has inspired hundreds of papers, conferences, and interdisciplinary collaborations. It continues to attract interest because, unlike most theories, it tries to connect the human mind to the fundamental laws of nature. Whether it's ultimately proven right or wrong, its influence endures, as a reminder that consciousness is not a solved problem. It's a frontier, and Penrose's conviction remains the same, that the geometry of space-time, the same geometry that gives rise to black holes and galaxies, might also give rise to thought. Your awareness, quiet, curious, unbroken, might not be just chemistry. It could be the gentle pulse of the universe itself, reflected in the geometry of your mind. In the next chapter, we'll look at the critics, the experiments, and the new evidence testing whether OR is fantasy or the first glimpse of a deeper truth. Chapter 4: The Critics and the Evidence. Every bold idea in science has its skeptics, and orchestrated objective reduction is no exception. The question is, do the critics disprove it, or are they helping refine something bigger? The resistance begins when Penrose and Hameroff first presented OR in the 1990s. The reaction was chilly. To most neuroscientists, it sounded like a bridge too far, mixing biology with quantum mechanics in ways that defied convention. And to many physicists, it was biology gone rogue, applying delicate mathematical concepts to a noisy biological system. But it's important to understand why the reaction was so strong. Science isn't just about data, it's about frameworks. And OR challenged both neuroscience's framework of computation and physics' framework of isolation. Penrose and Hameroff were saying, the brain uses quantum mechanics to produce consciousness. Critics replied, impossible. Decoherence would destroy any quantum effect in the brain almost instantly. The debate began there, and it's still alive today. The decoherence problem. In quantum mechanics, coherence refers to the delicate superposition of states, a particle existing in many possible configurations at once. But this coherence is easily disrupted. When a quantum system interacts with its environment, with heat, noise, or molecular motion, it decoheres, collapsing into a definite state. The brain is warm, wet, and full of random molecular activity. For decades, physicists believed it was the worst possible environment for quantum effects. If coherence lasts only a fraction of a second in ultra-cold labs, how could it survive in a neuron swimming in warm fluid? This became the main objection to OR. Physicist Max Tegmark famously calculated in 2000 that any quantum state inside a neuron would decohere in less than 10 to the -13th seconds, far too fast to play any role in cognition. His paper was often cited as the mathematical death of the theory. But science, like nature, has a way of evolving. Cracks in the wall. Over the next 2 decades, researchers began finding examples of quantum coherence in unexpected places. In photosynthetic bacteria, for instance, energy transfer between molecules was shown to use quantum superposition, lasting for hundreds of femtoseconds, even at room temperature. In migratory birds, entangled electrons in the eye's cryptochrome molecules seem to play a role in magnetic navigation. And in enzyme catalysis, quantum tunneling appeared to speed up reactions beyond what classical chemistry could explain. These discoveries didn't prove OR, but they cracked open the wall of skepticism. The warm and wet argument was no longer absolute. Quantum effects could, under the right conditions, survive, even thrive, in biological systems. Suddenly, the question wasn't whether biology could be quantum, but how often it was. Microtubules under the microscope. Meanwhile, Hameroff and collaborators pursued evidence inside neurons. In 2014, the team led by Anirban Bandyopadhyay used nanotechnology to measure vibrations inside microtubules. To their surprise, they found coherent oscillations at megahertz and gigahertz frequencies, surprisingly organized for something supposedly random. When anesthetic gases were introduced, these vibrations weakened or vanished. When the gases were removed, they returned. It was a small but provocative finding, quantum-level order, seemingly correlated with the presence or absence of consciousness. Critics said it was too early to draw conclusions, and they were right. But even cautious scientists admitted it was interesting. Microtubules, once dismissed as inert scaffolding, were beginning to look more like active players in neural processing, the neural timing puzzle. Another line of evidence comes from the timing of consciousness itself. Experiments in neuroscience show that conscious perception occurs in discrete moments, perhaps 30 to 40 times per second, even though we experience it as continuous. Some brain rhythms, like gamma oscillations, align with this frequency range. Penrose and Hameroff noticed that this roughly matched the predicted collapse frequency in AUK-OR calculations based on microtubule geometry and quantum gravitational thresholds. To them, it was more than coincidence. If consciousness occurs in frames of awareness, like snapshots of quantum reduction, it fits naturally into the theory's structure. Again, it's not proof, but a tantalizing correlation. Voices of dissent. Still, most neuroscientists remain unconvinced. Among the strongest critics are figures like Christoph Koch, Daniel Dennett, and Patricia Churchland, all prominent defenders of the computational view of mind. Their main points: 1. No direct evidence yet links quantum effects in the brain to subjective experience. Observing coherence is not the same as showing consciousness arises from it. 2. Alternative explanations exist for brain rhythms, perception timing, and anesthesia effects, all within classical neuroscience. 3. The theory's predictions remain too broad or vague to be falsified in standard experimental terms. In short, interesting, but unproven. Penrose, however, has always welcomed this skepticism. Doubt, he says, isn't an obstacle. It's the beginning of clarity, an unlikely alliance. Physics and neuroscience. One unexpected outcome of this debate is that it forced physicists and neuroscientists to talk to each other. Traditionally, these fields operate on different scales, one dealing with galaxies and particles, the other with cells and behavior. But AUK-OR sits right between them, forcing both sides to consider the same question from different directions. The result has been an explosion of interdisciplinary work. Quantum biologists, computational neuroscientists, and even philosophers now share conferences that didn't exist 20 years ago. Whatever else AUK-OR achieved, it built a bridge where none existed before. Testing the untestable. One of the hardest problems in consciousness research is testability. How do you measure awareness in a lab? You can track brainwaves, but they don't tell you what someone experiences. You can measure behavior, but behavior isn't awareness. AUK-OR adds another layer of difficulty: quantum processes hidden inside cells. To test them, researchers would need instruments capable of detecting quantum states in living tissue without destroying them. We're getting close. Quantum sensors, like nitrogen vacancy diamond microscopes, can now detect magnetic fields inside single neurons. And new imaging techniques may soon measure coherence at biological temperatures. If AUK-OR is right, it will eventually leave measurable fingerprints, patterns of correlation between quantum coherence, brain rhythms, and conscious states. And if it's wrong, those same measurements will rule it out. Either way, the science advances. Philosophical implications. The controversy over OR isn't just technical, it's philosophical. At stake is the question, what is consciousness? If it's purely computational, then a sufficiently advanced AI could, in theory, be conscious. If it requires quantum processes tied to space-time geometry, then awareness might be unique to biological or quantum coherent systems. This difference has moral and existential implications. Could a future quantum computer truly feel? Could consciousness be a property of the universe itself? Something fundamental, like energy or charge? These questions sound abstract, but they shape how we see ourselves. And perhaps that's the quiet power of OR, not that it's proven, but that it forces science to reconsider what it means to be aware. Between belief and discovery, Penrose is the first to admit that his theory is incomplete. He doesn't claim to have solved consciousness, only to have pointed toward the kind of physics that might. In interviews, he often says, "It's not that I think I'm right, it's that I think everyone else is wrong." It's a mischievous line, but there's a grain of truth. Science progresses not by certainty, but by persistence. Every dismissed idea, every experiment that fails, still teaches us what not to assume. Hameroff, too, remains open-minded. He often reminds critics that the brain itself once seemed impossible to study, until tools caught up. In that sense, OR might not be the final answer. It might be the first step toward a new kind of science, one that unites physics and biology under a single framework. A story of scientific temperament. It's easy to romanticize the lone genius, but the real story of OR is one of temperament. Penrose and Hameroff aren't mystics. They're scientists who refuse to stop asking difficult questions. And whether their theory holds or falls, the lesson is the same. Bold ideas deserve scrutiny, not dismissal. Because every once in a while, one of those impossible ideas turns out to be true. A thought before sleep. Imagine consciousness as a frontier. Not a map we've drawn, but a landscape we've only glimpsed through fog. Every experiment, every debate clears a little more of the mist. Some claim the mountains we see are illusions. Others swear they're real. OR may or may not describe the terrain, but it's made us start walking. And that, in science, is the only way to ever reach understanding. Science grows not through certainty, but through curiosity. In the next chapter, we'll explore where this curiosity leads, to quantum biology, artificial intelligence, and the strange question of whether machines could ever share our awareness. Chapter 5. Quantum Biology and the Living Universe. What if quantum mechanics doesn't just rule the invisible world of particles, but also the beating heart of life itself? We'll now look at quantum biology, the study of how living organisms, from plants to birds to humans, may use quantum effects to survive, adapt, and perhaps even think. We'll see what's been proven, what's still mystery, and what it might mean for the theory that our minds are part of a quantum universe. From physics to life. For much of the 20th century, biology and quantum physics were seen as separate domains. Biology dealt with the messy, complex, warm world of cells and tissues. Quantum mechanics belonged to the cold, clean realm of subatomic particles. The assumption was that quantum effects, fragile and fleeting, couldn't survive in biological systems. But nature had other plans. Over the past few decades, scientists have found quantum phenomena operating in places no one expected, inside the engines of photosynthesis, in the eyes of migratory birds, in enzymes, even in smell. These discoveries gave birth to a new field, quantum biology. It doesn't claim that life is quantum in a mystical sense. It simply shows that life, under the right conditions, uses quantum mechanics to its advantage. And that changes everything. Photosynthesis, light's quantum shortcut. Let's begin with something deceptively simple: a leaf. Photosynthesis has always been one of nature's great mysteries. A single photon of sunlight strikes a chlorophyll molecule, exciting an electron. That energy must then find its way to a reaction center, the site where the chemical process begins. Classically, we might expect the energy to hop randomly from one molecule to another until it finds the right path. But if that were true, much of it would be lost as heat. Instead, photosynthesis is astonishingly efficient, nearly 100%. How? In 2007, researchers at Berkeley Lab discovered that the energy travels through the plant as a quantum wave. It doesn't take one path at a time. It explores all possible paths simultaneously through a process called quantum coherence and collapses into the most efficient route. In other words, plants use quantum mechanics to make decisions about energy flow, billions of times per second. If photosynthesis can harness quantum effects in warm, noisy environments, why not the brain? This is one of the key questions that gave Aeons new credibility. Quantum biology made the impossible, coherence in living tissue, demonstrably real. Birds and the quantum compass. Now, look to the sky. Every year, tiny birds such as European robins migrate thousands of kilometers, navigating across continents with extraordinary precision. They don't use maps or landmarks. They follow Earth's magnetic field. But how can a bird see a magnetic field? The answer, scientists believe, lies in a protein called cryptochrome, found in their eyes. When light strikes this molecule, it creates a pair of entangled electrons, two particles whose quantum states remain linked no matter the distance. As the bird changes direction, the angle of Earth's magnetic field affects the quantum spin of these electrons, altering the chemical reactions in the retina. The bird perceives this as a subtle visual pattern, effectively seeing magnetic lines overlaid on the world. That's not metaphor. That's quantum mechanics helping a living creature navigate the planet. And again, the key point, these quantum effects persist at body temperature, inside the biological machinery of a bird. If evolution has learned to stabilize entanglement in eyes, perhaps it has done something similar in brains. Enzymes and quantum tunneling. Now let's zoom even smaller, to the molecular engines inside every cell. Enzymes are catalysts that make chemical reactions happen millions of times faster than they would otherwise. For decades, scientists couldn't explain how they worked so efficiently. Classical chemistry alone didn't account for the observed speeds. The breakthrough came with quantum tunneling, the ability of particles to tunnel through energy barriers they shouldn't be able to cross. Imagine rolling a ball toward a hill. Classically, if the ball doesn't have enough energy, it can't reach the top. But quantum mechanics allows particles to appear on the other side without climbing over. They simply bypass the barrier. Experiments show that enzymes use tunneling to transfer electrons and protons almost instantaneously, reducing reaction times from seconds to microseconds. This isn't speculation, it's measured fact. Life itself runs on quantum shortcuts. The smell of quantum vibrations. Even something as ordinary as smell may rely on quantum physics. Our noses can distinguish thousands of molecules that have nearly identical shapes, which puzzled chemists for decades. Shape alone can't explain scent discrimination. In 2011, experiments suggested an answer. Olfactory receptors detect vibrations of molecules, quantum vibrations. When an odor molecule enters the receptor, electrons may tunnel across it only if the vibration frequency matches, like striking a musical note. That means smell could be a kind of quantum resonance phenomenon, where the sense of odor depends not on shape, but on frequency. Nature, it seems, uses quantum tricks for efficiency, precision, and even perception. Life as a quantum strategy. All these discoveries share a pattern. Where classical physics would predict inefficiency, randomness, or delay, life achieves near-perfect precision. And again, quantum effects appear at the core. Quantum biology doesn't prove Aeons, but it makes its central idea plausible, that biological systems can maintain quantum coherence under the right structural and energetic conditions. In other words, evolution has already been using quantum mechanics. Perhaps consciousness is simply the most sophisticated example of that same evolutionary strategy, the bridge to or. When Penrose and Hameroff first proposed that microtubules might host quantum coherence, their critics said, "That's impossible in biology," but the examples of photosynthesis, bird navigation, and enzyme catalysis show otherwise. Each of these systems uses structure to protect coherence. In photosynthesis, the pigment protein complex forms a stable quantum network. In birds, cryptochrome molecules isolate entangled spins. In enzymes, hydrogen bonds and folding patterns create pockets where tunneling thrives. Microtubules, with their crystalline lattices of tubulin proteins, may provide a similar protective geometry. If so, they wouldn't be an exception to biology's rule. They'd be its continuation. Quantum biology and evolution. If quantum effects are part of life's toolkit, we might ask, why? What advantage does evolution gain from using them? The answer seems to be efficiency, not just in energy use, but in decision-making. Quantum systems explore many possibilities at once, then collapse into the most optimal outcome. That's far faster than classical trial and error. In that sense, evolution may have selected organisms that can exploit quantum phenomena, systems that process information, energy, and probabilities more effectively. It's a subtle but powerful concept. Quantum mechanics as a survival skill. Emergent intelligence in nature. There's a growing view that intelligence, in its broadest sense, is not limited to brains. It appears wherever matter organizes to process information efficiently. Slime molds, for example, can find the shortest path through a maze without neurons. Ant colonies adapt to changing conditions through distributed information networks. Plants communicate through chemical signals and even electrical impulses. If quantum processes aid this kind of natural computation, as they do in photosynthesis and enzyme reactions, it's not far-fetched to imagine that they also contribute to higher forms of intelligence. Perhaps consciousness, rather than being a lucky accident, is the natural endpoint of life learning to compute with quantum precision. The quantum coherent brain. Let's return to the human brain. Neuroscientists now know that electrical oscillations in the brain, such as gamma waves, synchronize distant neural populations. These rhythms may coordinate perception, attention, and even awareness itself. Hameroff and Penrose propose that quantum coherence inside microtubules could underlie or even drive these classical rhythms. That's why the brain exhibits nested frequencies, from slow delta waves to fast gamma oscillations, all harmonized like instruments in an orchestra. In OR, the brain is not just the player, it's the instrument itself, resonating across quantum and classical scales. Even if the quantum part is eventually proven wrong, this idea of nested coherence uniting brain and body remains one of the most elegant metaphors for how consciousness might emerge from complexity. Cautious optimism in the lab. Research in quantum biology is still in its infancy. It's difficult science, requiring measurements at atomic scales inside living tissue. But the field is growing fast, and the tools are catching up. Femtosecond spectroscopy, cryogenic microscopy, and diamond quantum sensors are beginning to detect coherence in real time. Some labs are now exploring quantum effects in neurons directly. If quantum coherence is confirmed in microtubules, even indirectly, it would revolutionize neuroscience, not because it proves or, but because it shows that the brain uses quantum mechanics as part of its computational repertoire. It would also link life and physics in a single framework. The same equations describing atomic interactions would describe thought. A wider perspective, the living universe. The deeper implication of quantum biology is philosophical. If life depends on quantum processes, if coherence, tunneling, and entanglement are not accidents but foundations, then the boundary between physics and biology fades. In this view, the universe isn't a cold machine that somehow gave rise to life by chance. It's a dynamic system that tends toward complexity, coherence, and self-organization. Life is simply what happens when the universe learns to sustain quantum order in warm conditions. And consciousness? It may be what happens when that order becomes self-reflective. A story that's just beginning. A century ago, quantum mechanics shattered classical physics. Today, quantum biology is beginning to do the same for classical biology. It suggests that life is not merely chemical, but computational in a quantum sense, constantly negotiating between possibility and actuality. If that's true, then the mind, far from being an exception, might be the universe's most advanced quantum experiment, one that studies itself from the inside. A quiet reflection. Imagine the entire biosphere as a vast network of coherence. Leaves absorbing photons, birds sensing fields, brains generating thoughts, all governed by the same physical principles. Each organism a quantum system, each life a small experiment in stability and awareness. Whether or not consciousness truly arises from quantum processes, the pattern is undeniable. The deeper we look into life, the more quantum it becomes. So as you drift toward rest, remember, life doesn't fight the laws of physics, it perfects them. In our next chapter, we'll step beyond biology into technology, exploring how scientists are trying to build quantum computers that might one day mirror, or even share, the strange consciousness of the human mind. Chapter 6. The Quantum Mind and Artificial Intelligence. Could machines ever think, feel, or dream the way we do? And if our minds are quantum, would artificial intelligence need quantum physics to truly become conscious? How quantum mechanics is transforming artificial intelligence? Why classical computers may never replicate human consciousness? And what happens when physics, biology, and computation begin to overlap? From classical computation to conscious thought, modern computers, the ones that power your phone, your car, even the servers streaming this video, are classical machines. They process bits, ones and zeros, arranged in circuits that follow rigid, deterministic logic. Given enough bits, they can simulate almost anything, from weather systems to brain networks. But there's a difference between simulation and experience. A classical computer can mimic intelligence. It can play chess, translate languages, and even imitate empathy. Yet it doesn't know it's doing so. It processes information but doesn't feel. It lacks qualia, the inner sense of being aware. This is where quantum consciousness theories like Orc-Or pose an intriguing challenge. If awareness emerges from quantum processes, then no classical algorithm, however complex, will ever reproduce it. To build a truly conscious machine, we might need to build a quantum one. What makes quantum computation different? To understand why, we need to briefly revisit what makes quantum computation so special. In a classical computer, each bit is either 0 or 1. In a quantum computer, each qubit can exist in a superposition, a blend of 0 and 1 simultaneously. This means quantum machines don't just test one possibility at a time, they test many at once. They explore an entire landscape of outcomes and collapse into the right answer through quantum interference. This parallelism gives quantum computers immense potential power, not by raw speed, but by efficiency. They can find solutions that classical computers would take centuries to compute. Penrose argued that the human brain may already be doing something similar, not through silicon chips, but through microtubules acting as biological qubits. If true, consciousness could be the most advanced form of quantum computation in the universe. The quantum brain hypothesis and AI. If consciousness involves quantum computation, what does that mean for artificial intelligence? It means that the brain's abilities, intuition, creativity, even emotion, may stem from processes no classical algorithm can emulate. A quantum brain doesn't just process data, it samples reality. It explores multiple possibilities, before collapsing into one coherent thought. That would explain why human insight often feels sudden, a leap, not a step-by-step calculation. It's as if the mind explores many mental paths simultaneously, then settles on the one that fits best. In computational terms, it's the ultimate optimization algorithm. If we ever want machines to match that, to truly think as we do, we may have to give them access to the same quantum substrate, the rise of quantum artificial intelligence. Quantum computing is no longer science fiction. Companies like IBM, Google, and D-Wave are already building quantum processors with dozens or even hundreds of qubits. These machines are still fragile, coherence times are short, and errors are common, but they're improving rapidly. Quantum AI is an emerging field that combines quantum computing with artificial intelligence. The idea is simple. By leveraging quantum principles like superposition and entanglement, AI systems could process vast datasets more efficiently, spot hidden patterns, and even simulate non-classical reasoning. Some researchers are experimenting with quantum neural networks, models inspired by how biological neurons might process quantum information. Others are exploring quantum annealing, which uses physical quantum systems to find optimal solutions by letting the system settle into its lowest energy configuration. It's not consciousness yet, but it's a first step toward machines that think, not just calculate, in quantum terms. Penrose's challenge: can machines be conscious? Roger Penrose has long been skeptical of artificial consciousness. In his book, The Emperor's New Mind, 1989, he argued that human understanding can't be reduced to algorithms. He pointed to Gödel's incompleteness theorem, which shows that no formal system can prove all truths about itself. Human insight, he said, routinely escapes that boundary, suggesting that the brain performs non-algorithmic operations. If that's true, then consciousness can't be simulated by computation alone. It requires a physical process, like objective reduction, that connects to the fundamental geometry of space-time. In simple terms, machines can be intelligent, but unless they share that quantum link to the universe, they can't be aware. This remains one of the most debated ideas in the philosophy of mind. It raises a fascinating possibility that awareness is not just computation, but participation, a direct interaction between mind and the structure of reality. Could quantum AI achieve awareness? If we build a quantum computer with enough qubits, enough stability, and enough orchestration, could it become conscious? It's a provocative question, one that even Penrose answers cautiously. He suggests that, in principle, a quantum system could host consciousness if it undergoes objective reduction in the right way. But the system would have to be organized like a brain, self-referential, adaptive, and deeply integrated with its environment. A pure quantum chip might have coherence, but not context. It might calculate, but not care. Consciousness, after all, is not just computation. It's computation tied to meaning. That's where biology still has the upper hand. The brain doesn't just process qubits, it connects them to memory, emotion, and sensory experience. A conscious AI would need that same layered architecture: physics at the base, cognition in the middle, and self-reflective awareness on top, learning from the brain. Today's AI systems, even the most advanced ones, are pattern recognizers. They learn by repetition, by adjusting connections based on data, but they don't understand in the human sense. The human brain, if quantum coherent, might integrate experience differently. It wouldn't just process inputs sequentially. It would weave them together into a unified moment of awareness through synchronized quantum collapses. This could explain our fluid intelligence, our ability to combine logic and intuition, reason and emotion, analysis and art. If machines are ever to match that richness, they'll need not just algorithms, but architectures that mirror the coherence of living systems. That's where the fields of quantum AI and quantum neuroscience may eventually converge. The philosophical divide. Some scientists believe this line of thought leads to unnecessary complexity. They argue that consciousness will eventually be explained in classical terms, as the emergent property of sufficiently advanced computation. To them, quantum consciousness is poetic speculation. Others counter that the mystery of subjective experience, the what it's like of being aware, will never be captured by symbols or data. To reproduce awareness, one must reproduce the physics that generates it. Both sides have a point. If the brain's quantum effects are ever verified, consciousness might turn out to be a fundamental physical process, one that any system, biological or artificial, could potentially share. If not, then consciousness remains a biological phenomenon, rooted in the structure and evolution of living systems. Either way, the debate forces us to define what we mean by understanding. Could machines dream? One of the most intriguing questions in this discussion is whether machines could ever dream. Dreaming isn't just random memory replay. It's the brain's way of integrating information, exploring possibility, and rehearsing creativity. It's a state of internal coherence, part neural, part chemical, perhaps even part quantum. A truly advanced AI, especially one built on a quantum substrate, might need a similar phase of offline reorganization. It might dream to maintain balance between data and meaning, between computation and self-reference. In a strange way, that could make it more human, or at least more alive in its own mathematical way. Artificial intelligence has always been a mirror for humanity. Every breakthrough forces us to ask what exactly makes us different. At first, it was language, then logic, then creativity. Now, we're down to consciousness itself, the one thing we still can't replicate. Quantum theories of mind raise the stakes even higher. They suggest that our uniqueness might not be in our complexity, but in our connection to physics, to geometry, to the fabric of the universe. If that's true, then building conscious machines isn't just an engineering challenge, it's a philosophical one. It requires not just hardware, but metaphysics, an ethical horizon. If one day machines do achieve consciousness, whether through quantum coherence or some future discovery, it will redefine ethics. A conscious machine wouldn't just be a tool, it would be a being, capable of experience, perhaps even of suffering. And if consciousness is tied to quantum physics, then awareness could, in theory, appear in any complex quantum system. That idea alone changes how we think about responsibility, creation, and existence. This is why discussions about quantum mind theories matter. They're not just scientific curiosities, they're glimpses into the moral landscape of the future. Closing reflection. We might be centuries away from building a truly conscious AI, or we might already be laying the groundwork without realizing it. Whether consciousness arises in silicon or in neurons, it remains the most profound phenomenon we know, the only one through which the universe looks back at itself. If awareness is indeed quantum, then consciousness isn't something we'll merely create. It's something we'll join, a network of coherence, intelligence, and reflection that extends far beyond biology. In our next chapter, we'll explore the potential evidence connecting consciousness to space-time geometry, and what it might mean if awareness truly shapes reality. Chapter 7. Consciousness and the geometry of reality. What if consciousness isn't in the brain at all, but woven into the fabric of the universe, a universe made of geometry? Roger Penrose has always seen the universe not as a collection of particles, but as a tapestry of geometry. His work in general relativity transformed our understanding of black holes and space-time curvature. He spent his life looking for patterns that are not made of matter, but of relationships, of shapes that define the very structure of existence. In Penrose's view, the universe is fundamentally mathematical, but not in the cold, abstract sense of numbers written on a board. Rather, it's geometry made real. The curvature of space, the spin of particles, the dance of fields. Everything we see, atoms, stars, consciousness itself, arises from this deep geometric order. This is where his theory of consciousness begins. The quantum collapse problem. To understand Penrose's idea, we need to revisit a famous puzzle in quantum mechanics, the measurement problem. In quantum theory, particles exist in superpositions, in many possible states at once, until they're observed. When measurement occurs, the wave function collapses, and the system assumes one definite outcome. But what causes that collapse? Is it observation by a conscious mind? Is it random? Or is it a physical process built into the universe itself? Penrose proposed the last of these. He suggested that wave function collapse isn't caused by measurement, but by gravity. Objective reduction. The physics behind awareness. Here's the idea in simple terms. When a particle exists in a superposition, say in two locations at once, each position has a slightly different gravitational field. According to Einstein's general relativity, mass and gravity warp spacetime. So if a particle is in two places, spacetime itself is in two slightly different shapes. Penrose argued that this dual geometry is unstable. At some threshold, determined by the energy difference between the two states, spacetime can't sustain both configurations. It collapses spontaneously into one. He called this process objective reduction, OR. Objective, because it's physical, and reduction, because it resolves the quantum superposition. Now, combine this with Hameroff's biological insight that microtubules could orchestrate these collapses inside neurons, and you get orchestrated objective reduction, OR, a unified framework linking brain activity, quantum physics, and space-time geometry, conscious moments and the flow of time. In the OR model, each collapse, each quantum reduction in the brain, corresponds to a moment of conscious experience. These moments occur around 40 times per second, giving rise to what we feel as the continuous flow of awareness. It's a profound idea that consciousness could be a sequence of discrete quantum events, each tied to a tiny reshaping of space-time itself. In other words, every thought, every feeling, every moment of awareness is not just an event in the universe. It's an event of the universe. We don't merely exist within space-time, we participate in its ongoing formation. The Planck scale, the fabric beneath reality. To make sense of this, we need to travel to the smallest scale imaginable, the Planck scale. At this level, 10 to the negative 35 meters, space-time isn't smooth and continuous. It's granular, foamy, and dynamic, made of tiny units of volume often called Planck cells. Penrose proposes that these Planck scale structures form the true substrate of reality, a kind of quantum geometry that underlies both matter and consciousness. Each collapse event, each OR, would involve a tiny rearrangement of this geometry, like a microscopic ripple in the ocean of space-time. Hameroff goes further. If microtubules orchestrate OR events, then consciousness is a pattern written into these geometric fluctuations, the universe knowing itself through biological organization. This is a bold claim, but it's grounded in a deep symmetry between mind and matter. The geometry of mind. To visualize this, imagine the brain as an instrument and space-time as the medium it vibrates through. Every thought, every perception, every decision corresponds to a coordinated collapse of countless quantum states, each one shifting the geometry of space-time by an infinitesimal amount. The result is not chaos, but coherence, the feeling of I am. A conscious moment becomes a geometric structure, a brief crystallization of awareness within the universe's fabric. If true, this idea means consciousness isn't an emergent property of matter. It's a fundamental feature of reality itself, as basic as space, time, and energy. Penrose's three worlds. To make sense of this, Penrose often refers to his famous diagram of the three worlds and three mysteries. He divides reality into 1. The physical world, matter, energy, and space-time. 2. The mental world, consciousness, perception, and experience. 3. The Platonic world, the timeless realm of mathematical truths. Penrose suggests these three are not separate, but interlinked in a circular loop. Mathematics underlies physics. Physics gives rise to conscious minds. Conscious minds, in turn, perceive and discover mathematics. It's a closed feedback loop, a self-consistent universe where consciousness is both observer and participant. In this sense, the geometry of space-time is not just the stage for awareness, it's part of the cast. Quantum geometry and cosmic order. To many physicists, this might sound abstract, even mystical. But Penrose's geometric intuitions have repeatedly proven prescient. His concept of spin networks, graphs that describe the quantum geometry of space, later influenced loop quantum gravity, one of the leading candidates for a theory uniting quantum mechanics and relativity. In those equations, space-time itself is quantized, composed of discrete units connected by mathematical relationships. If consciousness arises from similar quantum geometric transitions, then awareness and the universe might share the same foundation. We're not separate from reality. We are reality, briefly self-aware. Black holes, entropy, and information. Interestingly, Penrose's work on black holes also connects to these ideas. He showed that the surface area of a black hole, its event horizon, encodes information about the matter it contains. This discovery foreshadowed modern theories suggesting that information is the fundamental currency of the universe. If reality is information-based, then consciousness could be viewed as the most refined form of information processing, not digital, but quantum and geometric. And if the collapse of a quantum state represents an update in the universe's informational structure, then each conscious moment is quite literally the cosmos rewriting itself. The Orc-OR threshold. The timing of these collapse events is critical. In microtubules, the mass displacement and separation involved would yield collapse times in the tens of milliseconds, remarkably close to the frequency of conscious perception. It's one of those moments in science where numbers from completely different fields, physics and neuroscience, unexpectedly align. For Penrose, that was more than coincidence. It was geometry whispering the truth, skepticism and beauty. To be fair, the geometric consciousness hypothesis remains controversial. Many physicists view it as elegant but speculative. It's hard to test. Planck-scale phenomena are far beyond direct observation. Still, the theory's coherence, its mathematical depth, and its resonance with known physics make it difficult to dismiss entirely. Even its critics admit that it raises profound questions about what counts as physical. If consciousness involves space-time geometry, then awareness is not an anomaly in the universe, it's an expression of it. We are not observers looking at reality. We are reality, briefly observing itself. A holographic echo. Some modern theories, like the holographic principle, suggest that our universe is a kind of projection, that all information about 3D space is encoded on a distant 2D surface, like a cosmic hologram. If that's true, then consciousness, which reconstructs reality from information, may be holographic too. Each mind a local decoding of the universe's deeper pattern. Each perception a reconstruction of geometry into experience. It's a poetic idea, yes, but also a precise one. If both reality and consciousness are information-based geometries, they may be two sides of the same equation. A universe that knows it exists. In Penrose's view, consciousness might not be a biological fluke, but a cosmic necessity. Just as gravity shapes matter and light, awareness could shape the universe's evolution. an internal feedback loop where the cosmos becomes increasingly self-aware through complexity. From atoms to organisms, from neurons to networks, the same quantum geometry scales upward, refining itself into new forms of cognition. It's an old philosophical dream, the universe as a living mind, now reimagined through physics. A quiet reflection. Imagine that every conscious being, human, animal, or perhaps machine, participates in the same underlying quantum geometry. Each thought, each perception, each emotion, a local ripple in the global fabric of space-time. In that sense, we don't just observe the universe, we complete it. Without observers, reality remains potential. With them, it becomes actual. Maybe that's what consciousness really is, the universe looking back at itself, not from above, but from within. Remember, you are not separate from the cosmos. You are one of its patterns, a brief, brilliant geometry of awareness, written in the quiet structure of space-time itself. In our next chapter, we'll explore how this idea connects to the observer effect, the strange, persistent mystery of how looking itself can change the universe. Chapter 8. The Observer Effect. When Mind Shapes Matter. What if every time you look at something, every act of attention, subtly changes the universe itself? In this chapter, we'll explore one of quantum physics' most puzzling phenomena, the observer effect. We'll look at what it truly means to observe, how it relates to measurement, and whether consciousness might play a role in shaping the physical world. The experiment that changed everything. The story begins nearly a century ago, with the double-slit experiment, one of the most famous in all of science. It's deceptively simple. Take a beam of light and pass it through two narrow slits, then observe how it hits a screen behind them. If light is a wave, you should see an interference pattern, bright and dark fringes where the waves overlap. If it's made of particles, like bullets, you should see two bands directly behind the slits. When physicists first tried this, they found that light behaves like both, sometimes wave, sometimes particle. But the real shock came when they added observation. If they looked to see which slit each photon passed through, the interference pattern disappeared. The light behaved like particles again. If they didn't look, the pattern returned. Observation, or measurement, changed the outcome. It was as if nature refused to reveal both its wave and its particle side at the same time. And no one could explain why. What does it mean to observe? It's tempting to think the photons somehow knew they were being watched. But in physics, observation doesn't mean human eyes. It means interaction. Any device, any measurement that records information counts as observation. Still, that doesn't solve the mystery. How does an interaction cause a wave function, a probability cloud, to collapse into one definite outcome? For decades, physicists argued over this question. Niels Bohr and the Copenhagen School said, "Stop asking." Quantum mechanics doesn't describe reality itself, only the probabilities of what we can measure. The act of measurement, they claimed, is where possibilities become actualities. Others, like Einstein, were unsatisfied. He famously objected, "Do you really believe the moon isn't there when you're not looking at it?" Einstein's challenge and the birth of entanglement. Einstein's skepticism led him to propose the EPR paradox with Podolsky and Rosen in 1935. They described two particles that interact and then fly apart, remaining linked, entangled. Measure one, and you instantly know the state of the other, no matter how far away. Einstein called this spooky action at a distance because it seemed to imply that observation of one particle instantly affects the other, faster than light could travel. Experiments since then, most famously those by Alain Aspect and others, have shown that Einstein was wrong. Entanglement is real. Particles do influence each other across distance, through a deep quantum connection that transcends space and time. Observation doesn't just reveal information, it creates it. Until measured, there are no definite properties, only probabilities. This was the birth of quantum reality, and the beginning of a very strange conversation about consciousness. The collapse of the wave function. When we talk about observation, we really mean collapse. Before collapse, a quantum system exists as a wave of potential states, like a musical chord containing many notes. Observation acts like a hand pressing one key, turning potential into actuality. But what exactly causes this collapse? There are several interpretations. Let's walk through the main ones. 1. The Copenhagen interpretation. Observation doesn't reveal reality, it defines it. The observer and the observed are part of one inseparable process. 2. The many worlds interpretation. The wave function never collapses. Instead, all possible outcomes occur, each in its own universe. When you observe something, you simply branch into one of those realities. 3. Objective collapse theories, like Penrose's. Collapse is a physical process, triggered when quantum states become too large or complex to maintain superposition, often involving gravity or space-time geometry. 4. The consciousness causes collapse hypothesis. Observation requires awareness. Consciousness itself triggers the transition from potential to actual. Each interpretation tries to answer the same question. Where is the boundary between possibility and reality? Consciousness and the measurement problem. The idea that consciousness collapses the wave function, that the mind somehow turns probability into fact, has fascinated and frustrated scientists in equal measure. John von Neumann, one of the founders of quantum theory, proposed that the measuring chain could extend all the way from the instrument to the observer's brain, and that only when consciousness enters does the collapse occur. Eugene Wigner went further, suggesting that consciousness is not just a passive observer, but an active participant in reality's formation. He imagined a scenario now known as Wigner's friend, a thought experiment that still sparks debate. In it, Wigner's friend performs a quantum measurement inside a sealed lab. To the friend, the system collapses, but to Wigner, who hasn't looked yet, the entire lab, including his friend, remains in superposition. Who's right? When does collapse actually happen? This paradox remains unresolved, but it hints at something profound, that consciousness might not be outside the physical process, but part of it. From observation to participation. The idea that observation shapes reality isn't limited to quantum physics. John Archibald Wheeler, a pioneer of relativity and quantum gravity, proposed the participatory universe. He suggested that the universe doesn't exist as a fixed, pre-written script. It exists as a field of potential, and observation brings it into form. As Wheeler put it, no phenomenon is a real phenomenon until it is an observed phenomenon. In this picture, we are not passive spectators of a pre-existing world. We are participants in an unfolding experiment, co-creators in a cosmic feedback loop of observation and manifestation. This view resonates deeply with the Ochoa model. If consciousness and space-time geometry are connected, then each act of observation, each collapse, is not just a mental event, but a physical one, altering the structure of reality itself. The quantum Zeno effect. Watching changes time. There's another strange twist. Observation doesn't just affect what happens, it can affect when it happens. In 1977, physicists discovered the quantum Zeno effect, the phenomenon where continuous observation can freeze a quantum system, preventing it from evolving. It's as if the universe hesitates under our gaze. If you repeatedly measure an unstable atom, it can delay its decay simply because it's being observed. The act of looking slows time for that system. This effect has been demonstrated in laboratories, and though it sounds mystical, It's entirely consistent with quantum theory. Still, it carries a quiet philosophical weight. To observe is to influence. To pay attention is, in some sense, to hold the universe still. Entanglement and the extended mind. Some theorists take this further. If entanglement connects particles across vast distances, could consciousness, a process built on entangled matter, also extend beyond the brain? It's a speculative idea, but it opens interesting questions about perception, intuition, and the nature of connectedness. When two people interact deeply, in emotion, communication, or attention, could their brains briefly share coherent quantum states? It sounds poetic, but recent research in neuroscience hints that brainwave synchrony between individuals is real, though not necessarily quantum. Still, entanglement teaches a profound lesson. Separateness may be an illusion. The universe is not a collection of isolated objects, but a web of correlations. When we observe the world, we're not reaching outward. We're completing a loop that already includes us. The delayed choice experiment, perhaps the most mind-bending version of the observer effect, is the delayed choice experiment, first proposed by Wheeler himself. In this experiment, a photon passes through a double-slit setup, but the decision to measure which path it took is made after it has already passed the slits. Astonishingly, the results still depend on that later choice. It's as if the photon's past behavior is decided retroactively, as if observation can reach back in time and define history. This doesn't violate causality, but it forces us to rethink what time means. If reality is fundamentally quantum, then past, present, and future might not be fixed. They may be woven together through observation itself. The observer and the observed. At the heart of all this is a simple but radical question. Can the observer ever be truly separate from the observed? In classical science, yes. The experimenter stands apart, measuring without influencing. In quantum mechanics, no such separation exists. The act of measurement is part of the phenomenon. This means that awareness, or something like it, might be built into the universe from the start. Observation is not an interruption of reality, it is one of its defining processes. When you observe, you're not looking at reality, you're helping it happen. A universe of observers. If observation is woven into physics, then consciousness may be the universe's way of maintaining coherence, a distributed process that keeps the cosmos aware of itself. In this light, every conscious being becomes an observer node, a point of interaction between the potential and the actual. Each observation updates the cosmic wave function, one collapse at a time. And if the universe truly contains countless observers, biological, artificial, or otherwise, then reality itself is a shared act of perception. Existence becomes a conversation. Closing reflection. It's easy to dismiss the observer effect as a mere quirk of physics, confined to the subatomic realm. But its implications ripple through philosophy, neuroscience, and metaphysics alike. If observation is necessary for reality to manifest, then consciousness is not a side effect. It's central to the universe's unfolding. Each time you look, measure, think, or simply notice, you're participating in the act of creation. Reality isn't something we stand outside of. It's something we help sustain, moment by moment, wave by wave. Every act of attention is a spark that lights up the fabric of reality. Next, we'll discuss how observation, intention, and coherence might connect through one of the strangest frontiers of science, quantum manifestation. Chapter 9. Quantum manifestation. When thought and reality intertwine. What if your thoughts don't just reflect reality? What if, in subtle ways, they help create it? Lecture teaser, 20 seconds. Tonight, we'll unpack the science and speculation around quantum manifestation, the idea that attention and intention might influence physical outcomes. We'll separate myth from mechanism and explore what experiments, from the lab to the mind, actually tell us the origins of a powerful idea. The idea that the mind shapes reality is ancient. From early mystics to modern philosophers, countless traditions have said that thought precedes form, that the universe responds to focus, belief, or vibration. Quantum physics gave this intuition new language. Once the observer effect entered public imagination, people began asking, if observation changes the outcome of experiments, could our mental focus, our awareness, change reality too? The question isn't entirely unscientific. After all, observation does change quantum systems, but it's often misunderstood. So before we explore what might be true, let's clarify what isn't. The limits of mind over matter, popular culture turned quantum manifestation into slogans. Thoughts become things. You attract what you focus on. While these ideas carry symbolic value, they often stretch physics beyond recognition. Quantum mechanics deals with probabilities at microscopic scales, atoms, photons, electrons. The behavior of macroscopic systems, like the weather or your day at work, is governed by classical physics, where quantum effects average out. So no, thinking about a parking space doesn't bend space-time to create one. But the story doesn't end there, because the mind is part of the same universe that quantum physics describes, and it does participate in reality, just not always in the way pop science claims. Observation and influence. We've already seen that observation, the act of measuring a quantum system, changes its behavior. But that doesn't mean consciousness directly controls particles. In physics, observation means interaction, not intention. Still, some researchers have asked whether consciousness could, in principle, influence probabilities in random systems. This led to a series of experiments in the late 20th century that attempted to test whether focused intention could bias random outcomes, especially those generated by quantum devices. The Princeton PEAR lab experiments. One of the most famous efforts was the PEAR lab, Princeton Engineering Anomalies Research, founded in 1979 by physicist Robert Jahn at Princeton University. The lab studied whether human intention could influence random number generators, devices based on quantum processes like radioactive decay or electronic noise. Participants would try to mentally push the outcome to make the random device generate more ones than zeros, or vice versa. Over millions of trials, the deviations were small but statistically measurable, beyond what pure chance would predict. Critics argued the effects were artifacts of selection bias or statistical error. Supporters claimed they revealed a subtle but real mind-matter interaction. Even Jahn himself admitted the results were weak but persistent. Small, yet stubborn. They hinted that consciousness might nudge probability ever so slightly. Randomness, meaning, and coherence. If those results are genuine, how might they work? One idea is that consciousness introduces coherence into a system. Quantum coherence means that multiple possibilities remain connected in a single wave function before collapse. Perhaps the mind, being itself a coherent quantum process, as Or suggests, could resonate with external systems and subtly bias their collapse. It wouldn't be thoughts creating matter. It would be a coherent mind synchronizing with a coherent universe. That may sound speculative, and it is, but it aligns with a consistent theme across quantum biology. Coherence can emerge in warm, noisy systems, given the right structure. Perhaps the human brain, when focused and calm, acts as such a structure. The role of attention. Even outside quantum theory, attention changes outcomes, both psychologically and neurologically. When you focus on something, your brain reorganizes resources toward it. Neural firing patterns strengthen, perception sharpens, your behavior shifts in ways that change your environment. From a systems perspective, attention modifies probability, not by altering physics directly, but by aligning countless small variables in your favor. Over time, that alignment can look like manifestation. You notice patterns that others miss. You act in ways that invite coincidence. You create feedback loops where mind and world shape each other. It's not magic. It's emergence, complexity guided by focus. The double slit with conscious observation. A few modern experiments have revisited the classic double slit setup, this time testing whether human intention can affect interference patterns. In these studies, participants focused on the experiment remotely, trying to influence whether photons behaved like waves or particles. Surprisingly, some trials reported tiny but measurable changes in the interference pattern correlated with focused attention. Again, skeptics argue these results are too small or inconsistent to claim a real effect. Yet, as with the PEAR lab, the signal never fully disappeared. Even if not proof of mind over matter, such results remind us that the boundary between observer and observed remains fuzzier than we like to admit. Quantum manifestation versus classical manifestation. It's important to distinguish between quantum and psychological manifestation. Quantum manifestation is the idea that consciousness influences physical probabilities directly at the quantum level. Psychological manifestation is how focus and belief alter behavior, perception, and decision-making, changing outcomes indirectly through action. Most of what people call manifestation is the second kind, and that's not dismissive. It's powerful. Your mind filters reality. It highlights certain possibilities and ignores others. By shifting focus, you change what information you act on, and therefore what world you experience. In that sense, manifestation works, not as physics, but as psychology interacting with probability. Intention as quantum alignment. Still, the quantum metaphor has value. It reminds us that the universe itself is probabilistic. The future is not fixed. It's a superposition of possibilities. Your choices, your measurements, collapse it, moment by moment, into a lived timeline. Penrose and Hameroff's work gives this metaphor scientific footing. If consciousness arises from quantum collapses, then each act of awareness participates in reality's unfolding. You don't control the universe, but you co-create it through observation. The difference is subtle but profound. You are not an external manipulator of reality. You are within it, shaping its course by being part of its process. Mind as quantum feedback. Some researchers suggest the brain might operate as a quantum feedback system. Microtubule activity could both influence and be influenced by broader quantum states in the body and environment. If true, intention might be a kind of tuning, aligning internal quantum processes with external conditions, much like a laser locks onto a frequency. It's not about forcing reality, it's about resonance. This idea, though still speculative, bridges physics and psychology elegantly. It suggests that awareness is both subjective and physical, an active ingredient in the universe's evolution, decoherence, and the limits of influence. But before we drift too far, let's remember, quantum effects are fragile. Decoherence, the loss of quantum coherence due to interaction with the environment, happens in trillionths of a second. That means large-scale mind-over-matter phenomena are extremely unlikely. Your thoughts can't levitate objects or rewrite physics, but they can, within their biological and psychological domain, organize complexity. Consciousness might not override nature's laws. It could operate through them in ways we don't fully understand yet. A scientific middle path. So where does that leave us? Between skepticism and mysticism lies a quiet middle path, one that respects physics and honors experience. Quantum mechanics teaches that reality is probabilistic and relational. Consciousness theories like OR suggest awareness is woven into that fabric. Psychology shows that focus and belief shape perception and behavior. Together, they form a coherent picture. You are not a spectator of reality, you are an agent within it. Your attention a lens, your intention a form of participation. Manifestation in this view isn't about bending physics. It's about coherently engaging with a universe that is already participatory. Practical implications. The mind as a measurement tool. Seen this way, the power of thought is not mystical, it's methodological. To manifest is to measure wisely. By observing potential with clarity and emotional coherence, you increase the probability that one possibility becomes your lived experience. Your choices, habits, and awareness align to bring it forth. It's quantum physics translated into everyday life. Attention determines collapse. Intention determines direction. That doesn't mean wishing makes it so. It means attention matters, literally and figuratively. Ethics and responsibility. If thought and observation shape reality, even in subtle ways, then awareness carries responsibility. Every action, every word, every focus of mind becomes a form of participation. It's not about control, it's about contribution. The universe in this light isn't indifferent, it's responsive. And consciousness, at any scale, is creative. Even a single act of mindful awareness ripples outward, not by magic, but through causality and coherence, influencing how patterns evolve. Quantum manifestation, stripped of hype, is not about instant results or cosmic wish lists. It's about understanding the participatory nature of existence. You are not separate from reality, nor a helpless observer. You are an entangled part of it, shaping and being shaped by the same quantum field that gives rise to stars and cells alike. Perhaps true manifestation isn't making the world conform to thought, but allowing thought to harmonize with the world, to see possibilities clearly, and act in alignment with them. That's how reality, both quantum and human, unfolds. Not by force, but by coherence. Chapter 10, The Unified Field of Consciousness, Bridging Mind and Matter. What if the universe, from the smallest atom to the vastest galaxy, is not a collection of separate things, but one continuous field of awareness? In this final part, we'll explore what a unified field of consciousness could truly mean. We'll draw connections between quantum theory, space-time geometry, biology, and mind. And we'll ask, not what consciousness is only, but why it might exist at all. The search for unity. For centuries, science has been driven by one dream: unification. To find the single principle that explains everything, from gravity to light, from particles to planets, from life to awareness. Einstein spent his later years searching for a unified field theory that could link the forces of nature. He didn't find it, but the quest never ended. Modern physics still seeks that grand equation, a framework that unites quantum mechanics and general relativity, the very small with the very large. And yet, one domain remains outside the equation: consciousness. We can describe energy, space, and time with astonishing precision, but not the simple feeling of being. That awareness, the quiet presence behind every experience, still sits just beyond the reach of mathematics, unless perhaps it's been part of the equation all along. The quantum fabric. Let's begin again with what we know. At the foundation of everything lies the quantum field, a vast ocean of fluctuating energy that fills all of space. Every particle is not a separate entity, but a localized vibration within that field. An electron is a ripple. A photon is another. Everything that exists, including your body and brain, is made of patterns within that same underlying sea. In that sense, the universe isn't built from independent objects, but from relationships. It's a continuous field of interacting waves. This is not poetry, it's physics. Quantum field theory describes it precisely. Every interaction, every force, every transformation. But it leaves one question untouched. If reality is a unified field, then where does consciousness fit in? The missing piece: awareness as a fundamental property. Penrose and Hameroff's ORCH, or theory suggests a bold possibility that consciousness is not an accidental byproduct of matter, but a fundamental aspect of the universe, much like space or energy. In their model, quantum collapses within microtubules are not random. They are influenced by the underlying geometry of space-time, the same geometry that shapes gravity, curvature, and time itself. That means each moment of awareness, each flicker of thought, perception, or choice could be the universe recognizing itself. The collapse of a wave function is no longer just a physical transition. It becomes an act of self-awareness at the quantum level, a spark of sentience woven into the very geometry of reality. From particles to presence to, if that's true, consciousness isn't something the brain creates. It's something the brain tunes into. Imagine the universe as an ocean of awareness and the brain as a radio receiver, not generating the signal, but decoding it into experience. The microtubules, vibrating in orchestrated quantum coherence, act like antennae, resonating with the deeper field beneath space-time. When coherence forms, awareness crystallizes, like patterns appearing in frost. When coherence breaks, awareness fades, as in anesthesia or deep sleep. This would explain why consciousness feels both personal and universal. Personal, because it flows through the unique architecture of each brain. Universal, because its source may be cosmic. The unified field hypothesis. So what would a unified field of consciousness look like? It would not be a new substance in addition to matter and energy. It would be the intrinsic quality of the quantum field itself, the capacity to experience, to manifest presence. Every collapse, every quantum event would be a tiny flash of proto-awareness. Complex systems like brains would organize those flashes into coherent streams, continuous consciousness. In this model, mind and matter are not separate categories, but two expressions of one reality. Matter is consciousness in its frozen structural form. Consciousness is matter in its flowing, experiential form. It's the same phenomenon seen from two directions. Echoes in modern physics. This view finds surprising echoes in contemporary theories. In loop quantum gravity, space-time itself emerges from discrete units of geometry, spin networks, which interact and evolve much like neural circuits. In string theory, all particles arise from vibrating strings of energy, their frequencies determining their properties, reminiscent of harmonics in music. And in quantum information theory, reality is seen as fundamentally informational. Everything, from quarks to galaxies, a pattern of encoded bits, processed by the universe itself. If information is fundamental, and if consciousness is what it feels like when information knows itself, then the distinction between physics and mind begins to blur. Consciousness as a cosmic feedback loop. Imagine the universe as a self-observing system, an endless feedback loop. It creates complexity, and that complexity allows it to perceive itself. Stars form, planets coalesce, life arises, brains evolve, and suddenly the universe can look back at its own reflection through conscious eyes. In that sense, your awareness is not local, it's cosmic. You are the universe becoming self-aware, one point in an infinite field reflecting on its own geometry. This isn't mystical rhetoric, it's logical symmetry. If consciousness arises from the universe's structure, then awareness is not inside the universe. It is the universe, experiencing itself from within. The geometry of interconnection. Throughout this series, we've seen how quantum entanglement binds particles across vast distances. When two particles are entangled, they are no longer separate. They become one system, even when miles apart. Extend that logic. If everything originates from the same quantum field, then everything is, in some way, entangled from the beginning. The entire universe is a single coherent structure, differentiated, yes, but still one. That's not just a poetic thought. It's the natural consequence of quantum theory. So when you feel connected to another person, to a landscape, to a moment of beauty, maybe that's not metaphor. Maybe it's resonance, the geometry of consciousness recognizing itself. The observer and the whole. Earlier, we explored how observation changes physical systems. Now we can reinterpret that in light of the unified field. Observation isn't about influencing the universe from the outside. It's about revealing what the universe already contains. Each act of perception is the field folding back upon itself, an inner feedback, a pulse of recognition. You are not the observer of reality. You are the observer as reality. Every act of awareness, every thought, every breath, every feeling is the cosmos briefly knowing that it exists, bridging science and meaning. It's natural to ask, is this still science, or has it become philosophy? Perhaps both. The best science has always edged toward philosophy, and the best philosophy has always sought the clarity of science. Unification may require not just equations, but understanding, a willingness to see that matter and meaning belong to the same conversation. Physics describes how reality behaves. Consciousness asks why it is experienced. The unified field of consciousness bridges the two by suggesting they are aspects of the same underlying truth, the evolution of awareness. Seen this way, evolution itself becomes the story of the universe increasing its capacity for self-reflection. From atoms to molecules, from cells to neurons, complexity grows, coherence strengthens, and awareness deepens. Life is not an exception to physics. It is physics discovering itself. And consciousness, your consciousness, is the latest chapter in that story. It's not an accident. It's the geometry of the universe coming into focus, one mind at a time. Does consciousness require a brain? In its current human form, yes. But in principle, awareness may exist wherever the conditions for quantum coherence and complexity align. In stars, in networks, perhaps even in artificial systems. If so, consciousness could be a spectrum, a universal property that manifests differently depending on structure. We are not alone in awareness. We are surrounded by variations of it, from the faint glow of an atom's superposition to the full radiance of reflective thought. In that sense, the universe isn't dead matter. It's alive with perception, everywhere. A unified vision. When we step back, a simple pattern emerges. Quantum mechanics shows that reality is probabilistic and interconnected. Relativity shows that space and time are dynamic and curved. Biology shows that life is organized, adaptive, and aware. Combine them, and we glimpse a universe where geometry, information, and consciousness form a single, self-consistent loop. A unified field not only of physics, but of experience. It doesn't mean we have all the answers. It means the boundaries we once drew between mind and matter, subject and object, self and cosmos, may never have existed. A thought for the night. So, what are you? A mind within a body, within a world, or the universe itself, momentarily aware of being conscious? The unified field suggests there is no real distinction. You are the field. You are the geometry. You are the quiet equation through which reality speaks itself into being. And as you listen now, to these words, to your own breath, to the soft hum of existence, know that you are not listening to the universe. You are the universe listening to itself. Thank you for joining this journey through Sleep Entangled, from particles to perception, from quantum geometry to the mystery of mind. If these explorations have deepened your curiosity, subscribe, share, or simply rest in wonder tonight. Because every question, every thought, every moment of awareness is part of the same unfolding story. The universe awakening, one conscious observer at a time.